first one. This will be the second one. Namely, you should not expect the same mathematical rigor during my lectures as on most previous lectures. But I think that it is fair to say that to some extent, many of the results I will show you are observationally confirmed. And again, to some extent, there is no better replacement for them. Okay, so I have divided my lectures to 4 parts. The first part will be some more motivation why this is a good idea to compute post-Newtonian corrections to the two-body, within the two-body problem in general relativity. The second part will be the main part, in which I will discuss the application of the ADM Hamiltonian formalism to two-point mass systems. And then, I hope that I will have time to do this. I will try to discuss 2 more specific applications of the formalism. The first one will be just to use Hamiltonian formalism to derive spin-orbit interaction in binary systems. And the last part will be devoted to the effective one-body approach to the two-body system. It does not work. It works in a second. You know why? Okay. I will start trying to explain why post-Newtonian two-body problem is important for gravitational wave astronomy. And the most important issue is, it is a difficult word, indispensability of match filtering in gravitational wave data analysis. We have seen this picture during the lectures of Adam Pound. So we are talking about the detection of gravitational waves coming from coalescence of 2 compact objects. What is measured is the dimensionless gravitational wave strain h of t, which is nothing but the ratio of the 2 things, namely the difference between the relative proper length changes of the interferometer arms. Yes, Lx and Ly are proper lengths of the 2 laser interferometer arms, and the L0, which is just the unperturbed length of each arm. We know that for LIGO detectors, we have 4 kilometer long arms, sorry. And for Virgo and Kagra detectors, this length is equal to 3 kilometers. The point is that this dimensionless gravitational wave strain is extremely small. This of the order 10 to -1 for the strong signals coming from coalescence of compact binary systems. But for example, for still not detected continuous type gravitational waves from pulsars, it is some 10 to -25, maybe 10 to -26, and we are still trying to detect them. Okay, we also remember that the typical waveform related to the coalescence of 2 compact objects consists of 3 parts. We have the adiabatic or circular in spiral phase, in which the frequency and amplitude is growing in time. Then we have the merger phase, and then we have the ring down of the resultant Kerr black hole. Because the signal is very weak, we need very sensitive search algorithm to find this signal in the detector's noise. So this is the typical picture. You see on the vertical axis, we have time in seconds. Sorry, on the horizontal axis, we have time in seconds. Whereas on the vertical axis, we have dimensional strain. This is the linear scale, but ticks are in the units 10 to minus 18. The blue thing is just the output of the detector. This is what the detector is actually measures. And what is the physical signal is this small red feature. In fact, situation is even worse because here we see that the duration of the signal is few seconds. That is not the case for the signals from coalescence of two black holes. Here we have tenths of 1 second only. And you see that amplitude of the signal is roughly 1,000 smaller than the amplitude of the instrumental noise. And as I said, this is a strong signal. So we need help from the statistical theory of detection of signals in noise. This is a well-developed theory. And the story is as follows, that each search procedure, each pipeline, defines a quantity which we call a detection statistic. And this quantity ranks the likelihood that looking gravitational wave signal is present in the data. Then one identifies candidate events which have high enough value of the detection statistics. They should be seen in all operating observatories. And moreover, their time of arrivals should be consistent with the interstate propagation times. Yeah, as far as we are thinking about the coalescent binary signals, the signals are very short. So the appearance of the signal in different detectors should be not at the same time. There should be some delay related with just the traveling of the gravitational wave front in the space through the Earth's. Then we estimate the significance of a candidate event by determining the quantity which is called false alarm rate. This is the rate at which detector noise produces events, which detection statistics value which are equal to or higher than the detection statistic value of this candidate event. This can be translated to false alarm probability. That is the probability of observing one or more noise events as strong as the candidate event in the observation period. So we have to check whether the noise is not able to produce the same value of the detection statistic which we would like to attach to the astrophysical signal. Now we have two main types of the search algorithms. Namely, first we have some searches for generic gravitational wave transients. It means that they operate without assuming any specific waveform model. Roughly speaking, they try to identify some excess power in the time frequency representation of the data. In a moment, we will see the example, which will illustrate this. And then we have match filtering searches, which use some relativistic models of the signals. The idea is very simple. Namely, we should correlate the data with the copy of a waveform we expect to find in the in the data, and this copy of the waveform is called a template. Okay, here is the example of the results of generic transient search from the first observing run called O1 of two LIGO detectors. Here, this is the famous first detected signal, GW150914. And we see here the time frequency analysis of the data. So again, along the horizontal axis, we have time. Along the vertical axis, we have some normalized amplitude of the frequency Fouriers of small chunks of data. So we see here some feature very clearly, yes? So it means that it seems that there is some excess signal, and moreover, we can even see the evolution of this signal over time, yes? That its frequency and also its amplitude, given by the different colors, is growing over time. Here, situation is much worse. Yes, on the left-hand side we see something, but here, it is difficult to say that there is some feature present in this image. But anyway, this is the result, as I have said, of this generic transient search. Yes, but if you use the match filtering search, exactly this number are related with the pipeline which is called GST-LAL pipeline. Please look at the false alarm rates. For this event, it is smaller than 1 event per 10 million years. This inequality sign means that it could be possible even to make more simulations to improve this number. But you agree that one false event per 10 million years is not good. The event lasts for some 0.1 second. And false alarm rate for this second event is the same. So from point of view of match filtering searches, the significance of both events are comparable. And this is why we are using match filtering searches. As I have explained just to you, match filtering has better sensitivity than unmodeled searches. Moreover, they constrain space of possible signals, what decreases false alarm rate. The idea is also not complicated. If you have more different independent possibilities to make errors, then the probability of making errors is greater as well. If you restrict the possible waveforms to some specific classes parameterized by few parameters, then the situation is better. And also the last advantage is very important, namely, you can use some signal-based vetoes to separate signals from transient noise. This is a very crucial thing because you can eliminate, because of this, many false signals. I will talk a bit more about this in a moment. But there are some challenges related to the match filtering searches. Namely, it loses sensitivity if templates do not match signal accurately enough. So we need accurate waveform models. Moreover, as you know, thinking about the gravitational wave signal from a coalescing compact binary system, the signal depends on several parameters, like masses of the binary black holes. There are spins, maybe some tidal parameters if we have, instead of black holes, neutron stars. So we need to construct not one template, by a discrete bank of templates, which are parameterized by the parameters of the signal. And construction of one accurate template requires accurate enough solution of relativistic two-body problems. And this is another story. But before this story, I will tell more on this match filtering search in the simplest case to give you impression about this deduction statistic. So this is one of possibilities. Let us imagine that we have some template h of t. This is theoretically predicted response function of the detector to gravitational waves coming from coalescence of compact binary objects. And then we have the data S of t. Here the statistics is the so-called signal to noise ratio, which is given by this formula, where this inner product is just the correlation, but this correlation is defined in the frequency domain. So it is defined here by this integral. F is the frequency of the signal, tilde means Fourier transform. And this correlation between the data and the signal is weighted by power of the noise. Exactly, to be precise, this is so-called one-sided power spectral density of the detector's noise. Here there is some small technical issue. Mainly we have here this exponent where TA is the time of arrival. Just looking for this integral means that we can check this correlation or compute this correlation for many different times of arrivals using the Fourier transform algorithms. Especially fast Fourier transform is very valuable to shorten the time of computation. And if in the chunk of data given here is this signal, performing carefully this integral for different values of TA, we obtain some peak when this TA will cover the real time of arrival of the signal to the detector. So we just maximize this correlation with respect to the time of arrival of the signal, and the maximum value is the value of our detection statistic. Moreover, you see that here you can obtain very easily false large value of this thing. You see, in the data there is a lot of peaks. There are different reasons for these peaks. So let us imagine that in the resonate frequency range you have a large peak, and this large peak can make this integral quite large, even if this correlation is outside this peak very poor. And for this, you need some extra thing. This is this signal-dependent veto. So you can just check whether the distribution of the signal into different frequency bands is consistent with the what we expect from the theoretical template. Okay, and because of this, in fact, it is reasonable even to claim that we detect the signal if we have only one operating detector. Yes. Without this, it would be very difficult to confidently say that we can detect such small signal using only one detector. But if we have two detectors, then of course we expect, and if they are operating smoothly at the same time, we of course expect that the signal will occur in both detectors. And again, as I have already said, that the time of arrival of the signal will be say, for LIGO detectors, not larger than, say, 15 milliseconds, because 10 milliseconds is the maximum propagation time between these two detectors, and we can add some uncertainty in the measurement of the times of arrivals. And finally, if we have two detectors, what is the detection statistic is just the quadrature sum of the two signals to noise ratios taken from individual detectors. And this is some real life example. This is what was done in the observing run 01. The first observing run of the advanced LIGO detectors. The waveforms used, or the templates used in this search spanned 4-dimensional parameter space. Namely, they depend on two masses of the binary components and two dimensionless spins, kappa 1 and chi 1 and chi 2. But you see that we take only the modulus of these vectorial quantities. It means that, in fact, we assume here that during the inspiral, the spins of the coalescing black holes are parallel to the orbital angular momentum of the binary. Of course, you can check that also if the deviation from this assumption is not very large, then there is also a good chance to detect the signal. There was some restrictions on the individual masses, and all the templates are shown on this picture. In fact, this is the projection of the 4-dimensional space onto the plane spanned by the masses, yes? And there are different colors. Different colors means that different type of templates or different ranges of parameters were used. For example, the green one is templates for the double neutron star signal, and this was just the post-Newtonian in-spiral waveforms computed to the 3.5 post-Newtonian order. What does it mean? I will explain carefully very soon. The rest, namely the blue or the orange one, was the full in-spiral plus merger plus ring-down waveforms constructed by means of the one-body formalism. What is interesting is that some 250,000 templates were used. And in the newer observing runs, this number of templates is rapidly growing. And now, construction of bank of templates requires multiple integration of partial differential equations. If you would like to produce such templates by numerical relativity approach, or ordinary differential equations if you use the approximate results. There is a technical term quite often used by people involved in this subject, approximate analytical relativity. And this was already stressed by Adam Pound in his lectures. In the nearest future, it is absolutely not possible to prepare banks of templates based on purely numerical results because of the number of these templates. So we need to solve two-body problem in general relativity. And there are different approaches to do this. Of course, maybe the most accurate one is numerical relativity approach, but it is a quite young area of research in that sense that the first successful waveform was obtained only in 2005 by Pretorius. And we have approximate analytical methods. Post-Newtonian ones, post-Minkowskian ones, or black hole perturbation cell force-based approach, which was discussed in Adam Pound's lecture. Again, this adjective analytical technically means here that this method rely on solving explicit, that is analytically given, ordinary differential equations. Contrary to full numerical relativity simulations in which you solve the full system of partial differential equations, that is Einstein equations. The time difference in the performing this task is enormous as you want. And still we have effective one-body formalism, which is something different. It is not ab initio method. It combines just the result of different approaches, all in fact approaches in some consistent way. You can ask questions. Yes? Yeah, but this degeneracy is only the leading order waveform. You see, if you would take the so-called Newtonian waveform, then really it depends only on masses through the so-called shared mass. But already adding 1 PN correction to it give you different dependence on the masses. Okay, so it's time to say what we mean by post-Newtonian expansion. This is weak field and slow motion expansion of general relativity. So the zeroth order expansion is just the Newtonian gravity. And by NPN order correction, we mean correction of the order V over C to the power 2n, where V is typical relative velocity within the source. We are trying to post-Newtonian, we are trying to describe in a post-Newtonian gravity. And moreover, we are interested only in a gravitationally bounded system. It means that V squares of the order of typical value of the Newtonian gravitational potential through the source. So again, the 1 PN correction is the correction of the order V over C squared. 2 PN is V over C to the power of 4. 3 PN is V over C to the power of 6, and so on. We have also post-Minkowskian expansion. This is the weak field, but not slow motion expansion. So this is formally expansion in powers of G of the gravitational constant. No, and we have the perturbation approach, which was discussed by Adam Pound. It is an interesting remark that if we know the NPM order expansion and post-Minkowskian order expansion, it means that we know also post-Newtonian expansion to the order of 1 smaller. So for example, second post-Minkowskian expansion cover all terms in first post-Newtonian expansion. And here we have, say, the picture which shows graphically the region of validity of different approaches. So we have numerical relativity, so not large mass ratios and not large distances. Then we have perturbation theory based on self-force approach. It means that the ratio should be large enough, and then we can cover the whole evolution independently on the distance between the bodies. And we have the region of validity of post-Newtonian theory. It means that, again, the mass ratio is arbitrary, but the distances should be large enough. And we have this green feature is the effective one-body model, which try to cover the whole space. And I should say that relativistic two-body problem is a very old one, and the literature on the problem is enormous. There are very many different approaches, and I will mention only few of them, and I will talk about only one of them. This, of course, which is related with my personal work, unfortunately. So I will talk about the IDM Hamiltonian approach, but there is also approach based on the direct iteration of Einstein equations in the harmonic coordinates. This is the group of Luc Blanchet and his collaborators, also very powerful group. Quite recently, there is also effective field theory approach, namely people from high energy physics started to use their Feynman diagram computer programs to compute dynamics of two black holes. Here we have such notions like advanced calculations of scattering amplitudes using generalized unitarity, double copy construction, aconal resummation, and advanced multi-loop integration methods. All this is very far from my field of expertise, so please do not ask about the details, but I can give you a lot of references, very fresh ones.
The merger of two black holes, basically you could stop at 5 loops because all the other connections of the scatterings basically gave purely quantum corrections. So if you want the classical result, I would ask you, that's where the power comes.
It's an interesting comment, but I will not comment on it. So, and also even more recently, there is still a new approach. It is extremely tricky approach. It is called tutti frutti approach, devised by Damour and his new collaborators, which combines all what you can do. That is post-Newtonian, post-Minkowskian approach, multipolar post-Minkowskian. This is the way in which the gravitational wave flux is computed. Also effective in theory results, gravitational self-force results, effective one-body approach, and Delaunay averaging. About this, I will talk more in my last part of the lecture. Okay, so now let us look what we need in the very simple case. That is, let us look how to produce the waveform from the post-Newtonian results. The simplest case means that we are restricting to the circular orbit. It is not a bad restriction, but because, as you know from the basic general relativity course, during the evolution of the binary system, eccentricity is diminishing much faster than the size of the orbit. Yes, so in very many astrophysical situations, we expect that when the gravitational wave frequency enter the observational band of the detector, the orbits will be very circular. So their evolution can be understood as a circular evolution of practically orbital circular orbits. And then the waveform is given by the very simple formula. It is the function of time. It is in fact the time measured at the detector location. And it depends only on one function of time phi of t. And this is nothing but the orbital phase of the binary. That's all. All you need is just to compute the time evolution of the orbital phase of the binary, and the phase of this waveform is just double of this orbital phase. And of course, you have also important modulation of the amplitude, where you have the frequency, angular frequency of the orbital motion. How to do this? It is a very nasty thing. I know that many people do not like this very much. Namely, you assume the validity of the balance equation. You can you take the binding energy of the two-body system, computed within the post-Newtonian approach as accurately as you are able to do this, and you equate the time derivative of it to the gravitational wave luminosity, that is to the rate at which the energy is radiated away from the system. And from this is in fact ordinary differential equations for the function phi, and solving to it, you obtain this function. Now, you have both sides post-Newton expanded. So on the left-hand side, the energy starts from the Newtonian energy, and then you have, of course, 1pn, 2pn, 3pn, and 4pn correction to this. This is in this framed things. I put all what is computed today, up to date. And on the right-hand side, you have also the luminosity expansion. Newtonian one, this is the leading order gravitational wave luminosity, which is equivalent to the famous quadrupole formula. And it is called Newtonian because to obtain the observable, you have to average the non-physical instantaneous gravitational wave luminosity over the orbit. And using and making this time averaging, you use just the Newtonian equations of motion. And this is why this leading order luminosity we call Newtonian luminosity. And that's all. So let us look at this formulae, just for fun. So first, some notation. We have masses of the bodies, the total mass of the system, the reduced mass, and very important quantity nu, which is called sometimes symmetric mass ratio. It ranges from 0 to 1/4. 1/4 is for equal mass binaries, and 0 is, say, test mass limit. Yes, where the mass of the one body is much smaller than the mass of the second one. And we can introduce dimensionless post-Newtonian parameter related to circular motion in this way, where phi dot is just the angular frequency in the orbital motion. And then post-Newtonian formalism gives you binding energy for circular orbits as a function of x and nu. This is the Newtonian thing, which is factor out, and then you have the fractional correction to this Newtonian energy. And we see that these corrections form a polynomial in x or logarithm of x, and all the coefficients of this polynomial depends only on nu. Very nice and simple formula. You have some transcendental numbers like Euler's constant, pi, and so on. This is the luminosity. The same story. This is a function of x and nu only. This is the Newtonian leading order luminosity. Then you have fractional corrections to it. Here we see that situation is a bit more complicated because we have a polynomial in square root of x. Yes, not only in integer powers of x, but the rest is the same. This is the very fresh result achieved by Blanchette groups and published in April this year. Okay, we are still making some preliminary considerations, so it is useful now to say that, in fact, usually post-Newtonian two-body problem contains two sub-problems, which are analyzed separately and solved by means of different tools. Namely, there is a problem of deriving equations of motion and a problem of computing gravitational wave luminosities. Here, I will not talk about spin-related effects and also no discussion about tidal effects. Both things are very important, but because of lack of time, I will not touch this. As I said, in the third part, I will speak a little bit about using Hamiltonian formalism to compute the spin-orbit interaction in binary systems. Okay, so let us look at the equation of motion stuff. History begins from Newtonian theory, then you have 1pn, 2pn, and here you have 2.5pn order. So you see that at certain moment we have the first odd in V over C order, and this is the first order in which radiative effects are visible. Then we have the rest. What is in red is worked out completely. What is in orange color is worked out almost completely, as far as I know, from different reasons. Here, what is interesting to say is that 5pn Hamiltonian is almost ready, but there is some problems, and this problem is quite persistent. Namely, in the effective one-body representation, this is just some technical issue again. This is the most compact representation of the dynamics, which is canonically equivalent to any other representation you imagine possibly to use. And there are three numerical coefficients which are controversial. That is, different approaches give different numbers. Also, 6pn is almost ready by tutti frutti methods. But here, there are at least 4 numerical coefficients which are still unknown, and there is nothing to be compared with. So, okay. But what is also important to say about the equations of motion, namely up to 3.5pn order, there is a nice split between the conservative equations of motion and dissipative equation of motions. Namely, Newtonian 1pn, 2pn, and 3pn equations of motion are purely conservative. That is, they are invariant against the change of the direction of time flow. Whereas 2.5pn and 3.5pn are purely dissipative. It means that they change this, the adherents change the sign when you change the flow of time, change the direction of flow of time. Okay, now luminosity. Luminosity starts from the Newtonian leading order quadrupolar formula. Why it is related to 2.5pn? Because of course, if you know the equations of motion, you know all. Because if the system is radiating gravitational waves, the back reaction changed the orbital motion of the system. So it is possible to obtain just from the equations of motion the luminosity. But to get the leading order luminosity, you have to know that 2.5pn orbital motion. So there is a 2.5 orders of shift between the luminosity and the equations of motion. So for example, if you know 3.5pn equations of motion, it is possible to obtain from this 1pn luminosity. This is quite physically interesting because then you can obtain the evolution of the phase, for example, of the orbital phase of the binary, not assuming the balance equation. It is not needed at all. All is encoded in the equations of motion. I will tell a bit more about this. A bit of history. Don't worry, I will be fast here. As I have mentioned, the first order in which the radiative effects appear on the level of equation of motion is 2.5pn order. So let us look at the first successful and fully complete and correct, because there was many non-complete and incorrect derivations. So of course we have Newtonian level. This is as you know, the year of publishing the Newton's Principia. Then we have the first PN correction, already made by Lorentz and Droste in 1917. But then, many years later, we have 2pn correction to the Newtonian motion. The first derivation was by Damour, and also in the same year he derived for the first time completely 2.5pn equations of motion. But I would like to put your attention on the next year, in which appeared I think the very fundamental paper by Damour, in which he derived the decay of the orbital period of the two-body system directly from the 2.5 pn accurate equations of motion, not assuming any type of balance equation. And this derivation, in some sense, at least to a large extent, according to the kinetic in this book, ended the so-called quadrupole formula controversy, which was quite vivid in the last century before you was born. Namely, many serious scientists doubted whether gravitational waves are real entities. For example, it was not clear that gravitational waves can transfer energy from the source to the observer, and so on and so forth. Of course, around late 70s and early 80s, the reason why people went back to the solving post-Newtonian equations of motion was the discovery of the binary pulsar, Taylor pulsar, and to understand why its orbital period is decaying. And we know that it is decaying because of gravitational wave emission. Then you have the 3pn order. And here, the motivation was related with the upcoming gravitational wave detectors. The people who are related with the idea of building laser interferometers, like Kip Thorne, Nobel Prize laureate, were sure that we need more accurate templates. It means that we need the next post-Newtonian order in equations of motion. This is the motivation. Then I fortunately ended my university study and I came to this business. So the first successful computation was in 2001 by this DJS staff. Then was another computation, both used Dirac delta sources and dimensional regularization. Afterwards, effective field theory approach computed also 3pn equations of motion. And what is interesting here to add that there exists only one pure three-dimensional derivation. This is derivation by the Japanese scientists Ito and Futamase, and they use some extended body model with strong field point particle limits. So in some point in their calculation, they shrink their bodies to the point particles and used a surface integral approach, which in fact is some modification of the famous Einstein-Infeld-Hoffmann approach to solving equations of motion in general relativity. Then we have 4pn stuff. I am trying to convince you that I am competent in what I am saying about. So again, the first complete derivation was 2014. 3 years later, the group of Blanchet also did this. And then we have two independent derivations within the effective field theory approach. Here is the story of the gravitational wave luminosity computations. And maybe I will finish with this simple timeline for the balance equations from which you can compute the phase evolution of the binary system to some fixed post-Newtonian order. Please look at the first line. So we need that starting from 2004, it was possible to compute templates up to 3.5 pn order. And as you have seen in this 01 template picture, exactly this kind of templates were used during this first run called 01. For the next pn order, you had to wait almost 20 years. Because only after completing this, it is possible to compute the orbital phase evolution up to 4.5 pn order. So as you see, this is the second warning that things are not very easy to compute. And a few words about the general bibliography, and then I think we can make a 5 minutes break. Let me start from the extant book by Major, a very useful and very complete book, Gravitational Waves, in 2 volumes. Then there is a book by Krulak and myself about gravitational wave data analysis, but in some introductory chapters, you have, say, introduction to two-body problem as well. There is a very useful but quite technical review article by Damour about the problem of motion in Newtonian and Einsteinian gravity, much shorter and newer article available in the archive, also by Damour, and 3 review articles taken from Living Review in Relativity. So I think that this would be a very good starting point for almost all what is related with equations of motion related to the two-body problem. Okay, so let us make 5 minutes break now. Do you hear me? Yes. Okay, this is the plan of the second part of the lecture, the main one, as I have said. And you see, I will start from the following thing. Namely, you see here that I use subsections. And the beamer does not work properly with subsections. So yesterday evening, I tried to find some solution using Google, of course. But I stopped doing this when I found the message from one beamer expert. He said, don't use subsections in the beamer. This is evil. So sorry for that. I used finally subsections. Okay, so I will start from some general remarks and summary. Then I will show you how conservative and dissipative matter Hamiltonians can be computed within the formalism. Then will be some more technical stuff, but without this, nothing can be computed, unfortunately. So some information about the regularization of ultraviolet and infrared divergences, but I will also mention about the beautiful check of the results, namely Poincare invariance of the obtained results. And I will end with the three-pin accurate Delaunay Hamiltonian derivation. This Delaunay Hamiltonian, that is the Hamiltonian expressed in terms of the so-called Delaunay variables, which are action angle variables, is needed, it will be needed then in the part devoted to effective one-body approach. Then I will finish by some open issues in the post-Newtonian two-body problem, and then calculemus. So there will be a set of exercises for you. And that's all. You see, this is the subsections. I shouldn't warn you. Again, it stopped to work. I do hope.
Because of subsection.
I don't know. Okay. No, but now it works. Okay, so maybe.
So don't go to that one.
Yes, okay, okay. This was this evil, I think. Okay, so another, you see, not very useful for you remark that many of the results I will show was done in the collaboration of myself with Thibaut Damour from France and Gerhard Schaefer from Germany. sometimes I call this collaboration the Weimar Triangle collaboration because it united scientists from France, Germany, and Poland. And, well, if you can see some difference between this photo and what you are seeing now, the explanation is simple enough. Namely, I was here some 20 years younger. That's all. Oh, okay, so general remarks and summary. We consider a system of 2-point masses. That is monopolar point-like bodies which interact gravitationally according to general relativity theory. And as I have already mentioned, spin and tidal related effects I will not discuss here, but the formalism can cover both. And there are well-developed extensions of the formalism to cover both spin-related effects and tidal interactions as well. We model point masses by means of Dirac delta distributions. So I will use the energy momentum tensor, which will contain Dirac delta distributions. We employ the ADM canonical formalism not in the free, but in capital D space-time dimensions. So small d is the dimension of space. This is because the only up to now way of removing ultraviolet divergences is to use dimensional regularization. Then we work in asymptotically flat d+1 dimensional space-time. And we use, to some extent, I would say, you will understand why this remark I am making now, asymptotically Minkowskian reference frame or almost Cartesian reference frame, different names can be used. So we have the time coordinate and space coordinates. Now, important thing that completely in a different way, we treat the conservative effects and dissipative effects. So we will have to solve perturbatively equations for the field degrees of freedom. And then in the case of conservative dynamics, we will use time symmetric green functions, that is half retarded, half advanced green functions. Whereas for the dissipative dynamics, we will use retarded green functions only. And the result is as follows. We unambiguously computed conservative Hamiltonians at Newtonian, not surprising, 1pn, 2pn, 3pn, and 4pn orders, and dissipative Hamiltonians at 2.5 and 3.5pn orders. So we worked out all post-Newtonian stuff up to 3.5 post-Newtonian order including. As I have said, Dirac delta sources lead to ultraviolet UV divergences. That is the divergences related with the location of the particles. Yes, many field functions depend on the position of the particles, and they are they depend on the field, say, point, and they are singular when this field point approaches the position of the particle. And as I said, we need a dimensional regularization to resolve them. And there is the most complicated stuff, namely there are also near-zone infrared divergences, and they are linked to the so-called tail effects, which are non-local in time. And to regularize these divergences, we needed a new time scale. And the result of the regularization was ambiguous. The ambiguity is expressible in terms of one numerical constant. And this constant was resolved by using some Dion near-zone information. In fact, the information computed within the gravitational self-force approach. This also was mentioned by Adam Pound in his lectures. Why Dirac deltas? I think that this is the most important thing. They simplify considerably simplifies computations, which are still very, very complicated at higher post-Newtonian orders. But we can also tell here about the effacement principle, first proved probably by Damour, but then proved by also other people. Namely, if we have compact and non-rotating bodies, you can just mathematically prove that there should be no information about the internal structure of the bodies up to the fifth post-Newtonian order. So, for example, at fourth post-Newtonian order should be no difference between the equations of motion of the neutron stars or black holes. And what is well known for some people, and also this is related with the phenomenon of punctures about which Adam Pound was talking about, namely that Dirac deltas can model sources for black hole spacetimes, yes, which are in a usual approach the vacuum solutions of the Einstein field equations. So you can solve Einstein field equations with some distributional sources and recover this vacuum black hole solutions. For example, this can be done for the Schwarzschild, and as I checked, there is a huge literature on this. But what is maybe less known, for example, there is a very useful for numerical relativity Brillinkquist solution of initial value problem, which is time symmetric. And it can be formulated, for example, for two black holes. This is illustrated by this picture. And also this originally derived as a vacuum solution of the constraint equations. You can easily recover this as a solution with the distributional source. And of course, we have nice a posteriori argument that using delta sources and dimensional regularization give unique conservative equation of motion up to fourth post-Newtonian order, and most probably also unique gravitational wave luminosities up to 4.5 post-Newtonian order. I say probably because, as I said already, some very complicated results were achieved only by one computation, and there is nothing to compare with. And there is a lot of errata on this. Okay. Oh. On my computer it worked. I don't know. Sorry. No, not this. You must. Okay. Okay. So now I will present in more detail the formalism. Let me start from some technical result, but it is quite important for careful audience. Namely, in dimensional regularization, we have a natural length scale denoted here by L0. And this scale relates the Newtonian constant and the gravitational constant in d-dimensional space-time. Yes, epsilon is just the difference between the dimensionally continued dimension d and free. Why it is important? Because almost always I will work in the units where c is 1 and the dimensional gravitational constant is 1/60 pi. You know why it is 1/60 pi? I was surprised very much. This is that in normal units, the Hamiltonian is something like this. And here in 3 dimension, you have Laplacian of some field function. You will see it very soon. And this is the reason, yes? If you have this nice formula for the energy, then you should put c equal to 1, but also g equal to 1 over 60 pi. But anyway, going back to this, why this is important? It means that before computing the limit d goes to 3 or epsilon goes to 0, you have to recover all g's to have this L0 at your disposal. Okay, so some more notation. AB are particle labels, masses of the particles, positions, linear momentum vectors. Dot will mean just the Euclidean, but in general, d-dimensional scalar product. So magnitude of V is again the Euclidean magnitude of the D vector. And here I have this nice picture, you see, like in the textbook. The main thing is to distinguish between x1 and r1. So you see that you have the mass m1. x1 is its position vector, mass m2, and the device is not operating anymore. Okay. X is just the position of the any field point. So R12 is just the vector joining the bodies, and R1 is the field vector, field point, say, observed from the mass number 1, and the same is for R2. As usual, in any Hamiltonian formalism of general relativity, we split spacetime into following form, where n is the lapse function and I is the shift vector, and gamma is just the space part of the four-dimensional, of the D, sorry, of the D plus 1 or D, capital D dimensional metric. Gamma is determinant of this space metric. Canonical variables in the theory are matter variables and field variables describing the evolution of the gravitational field. As matter variables, we have just positions and momenta, as usual. Field variables consist of, again, space part of the D-dimensional metric, and its conjugate, the field momentum, can be expressed in terms of K ij tensor, which is the extrinsic curvature of the constant time slices in the space-time. Okay, now we have the ADM Hamiltonian, which is valid, as I said, in asymptotically flat space-time and in asymptotically Minkowskian coordinate system. And from this Hamiltonian, one can derive the full set of Einstein field equations. Here we have shift and elapse, and they operate as Lagrange multipliers here. And we have the famous surface term, which in fact will be the real Hamiltonian very soon. H and Hi are called sometimes super Hamiltonian and super momentum, and can be computed from this formulae. Of course, T mu nu is the energy momentum tensor, and G mu nu is, as usual, the Einstein tensor. So in the first step, we variate this Hamiltonian with respect to n and I, and as a result, we obtain the famous constraint equations of general relativity. And now all was said up to this moment is valid for any kind of matter sources. Of course, I use already the x and p as matter variables, but besides this, and here we use the energy momentum tensor describing two-point particles. This is exactly the D-dimensional version of the energy momentum tensor used by Adam Pound in his construction of punctures in spacetime. And we have the heart of the theory, the constraint equations, written already for two-body system made of point particles. So we see the d-dimensional Dirac deltas. Yes, and to be precise, R is the spatial curvature of the constant time slices. dj is the spatial d-dimensional covariant derivative acting on the field momenta, which is not a tensor, but to be precise, a tensor density of weight 1. And the most interesting thing is that these Dirac deltas on the source part of the equations are multiplied by some terms which depend on the metric, which is supposed to be singular at the position of the particles. So at this moment, you should replace this metric by some regular value of it computed on the world line of the particles. And I will explain you how this can be done, and at least up to the fourth post-Newtonian order, this can be done perturbatively and unambiguously. The next step is fixing the gauge. We use ADM-TT gauge. It means that the space metric is the sum of two parts. The first is just the isotropic metric, yes, which is parameterized by the single function phi. And the second part is the transverse and traceless part of the metric, HTT-IJ. Traceless means here, and transverse leads to this extra condition. And the second gauge condition is that the Euclidean trace of the field momenta is zero, vanishes. Because of this, you can split the field momenta into longitudinal part and TT part again. So these conditions are fulfilled also for this TT part of the field momenta. And you can express this longitudinal part in terms of one vectorial quantity only. Yes, so it has 3 functional degrees of freedom. The TT projection can be achieved by means of this terribly looking non-local in space integral differential operator given by this formula. As I have said, the theory as such is formulated in asymptotically flat spacetime. It means that we should require some asymptotic behavior of the field functions, and they are given here. All is nice up to the moment at which we try to compute the propagating, say, degrees of freedom of the gravitational field. As you will see, they fulfill some wave-like partial differential equations. So their solution naturally contains some retardation, T minus R, for the time argument. But to be consistent with the post-Newtonian scheme, we have to expand these retardations. Yeah, because post-Newtonian theory means that at each post-Newtonian level, the gravity is propagating at infinite speed. And then the problems begin, because after doing this, you see that next terms start to behave badly at infinity. Yes, in 3 dimensions, say, this term is constant in space. It can depend on the direction n. The next term already diverges like r at infinity in 3 dimensions, and we can live with this. There is no escape, and this is one of the sources of infrared divergences. Okay, so time to start make post-Newtonian expansions. This expansions is needed for perturbative solving the constraint equations. So the first step is to express using constraint equations, the functions phi and vi in terms of the canonical variables of the theory. And to do this, we use the post-Newtonian approach. So as I have already said, we assume that this is true, that this quantity is very small. Because we use units in which C is 1, it means that we should treat V as a quantity of the order C2 minus 1. And the mass, it is the most convenient way of counting, say, orders, believe me, as a quantity of the order C2 minus 2. Then you can easily check, maybe not so easily, but you can check that you have this behavior or disordering in inverse powers of C of all quantities entering the formalism. M, linear momentum. This is mass time velocity. So C2 minus 1 times C2 minus 2. This is why we have C2 minus 3. Phi start at C2 minus 2. HTT is C2 minus 4, and so on. And then we expand also phi and vi in the post-Newtonian series. This is the beginning of these expansions. And after doing this, we have, say, a system of elliptic equations fulfilled by this phi and vi, symbolically written here. All these are elliptic type equations. Yes, so we have here non-propagating degrees of freedom of the theory. Just to be a bit more concrete, this is not easy, but it is possible to show that up to the 3pn and including 3pn order, you can express the Hamiltonian density by means of only these 6 functions. And I have written here the equations fulfilled by these functions, and look at that they are very simple with the exception of the last equation. In fact, this HTT4 is the leading order HTT. And what is a technical remark that all these functions can be computed easily in the dimensions with the exception of the momentum independent part of this HTT4. This is hard to compute in the dimensions. There are some expressions for this, but they are not very useful. They are typically of the form of double hypergeometric functions, or double series of hypergeometric functions, or series involving Appel functions. So, yeah. Okay, now about solving these equations. The solving is using the so-called inverse Laplacian technique. It means that we use some basic relations, which are just solutions of the appropriate Poisson type equations. Yes, if we have the source of the Dirac delta type, then its basic solution is given by this. Kappa here should be not K. Kappa is given here. It is 1 over 4 pi in 3 dimensions. And we have, say, the generic inverse Laplacian of the power function for any lambda. And using this, you can easily find the 5 of these functions. The computation is quite natural and very easy. This is e.g. how you can find phi2 in the dimensions. This is the whole Newtonian theory, in fact. Yeah, with this up to a factor, it is exactly up to a numerical factor, something like 1/4. If I will remember, it is just the Newtonian gravitational potential in the dimensions. Okay. Now we use both the gauge conditions and constraint equations. And using them, you can reduce the initial Hamiltonian of the theory to this form. some more algebra is needed to do this. But anyway, we obtain at the very end the so-called reduced form of the ADM Hamiltonian, which depends only on the canonical variables, matter variables describing the point particles, and the propagating degrees of freedom of the gravitational field. And please look how simple it is. It is just the Laplacian of the field function phi. Yes. So then you can make the post-Newtonian expansion of this, and you have post-Newtonian expansion of the Hamiltonian. All you need is just to compute this. And what is important that this reduced Hamiltonian contains the full information both on the equations of motion for the particles and also about evolution equations for the field degrees of freedom. Here you should know that we have to use this TT projection operators on the right-hand side of these equations. And what is interesting that the Laps and shift functions are completely decoupled from the theory. We do not need them to compute equations of motion, to compute evolution equations of the gravitational field degrees of freedom. Of course, from the initial Hamiltonian, follow the equations of for shift and Laps, and if we needed them, we can go back to these equations and solve them. No problem. Oh, no, but sorry. You see, evil is evil. This I know. I will never use subsection in the BIME from today. I promise. Okay, thank you. Let us look for the field equations of the theory. And in fact, if we are interested in 4p accurate reduced Hamiltonian, it is enough for computing field equations to consider 3p accurate reduced Hamiltonian only. Let us look at his structure. Small h means here the Hamiltonian density. And this Hamiltonian density contains the rest mass contribution, Newtonian contribution, 1pn, 2pn, and 3pn contributions as well. Looking carefully at the form in which these TT variables appear in individual Hamiltonian densities, you can easily show that the field equations look as follows. You have the equations for the time derivative of HTT and the equations for the time derivative of TT. This is a simple exercise. And this is more explicit form of these equations. And you see that by differentiating with respect to time the first equation and using the second one, one easily combines these two equations into the form of the wave-like equations, where box means the flat space time D'Alembert operator. But the source term is very complicated, and of course the leading order terms do not depend on the TT variables, but at some moment you have TT variables involved in them. So this is a very complicated nonlinear equations, in fact. So the procedure is that you should first find HTT and then solving the first equation again with respect to pi TT, you obtain the field momentum, which is given by this formula. And for example, only on this level, in fact, you can recognize that the leading order HTT is at C⁻⁴. I haven't mentioned that this numbers in parentheses denote the order in C⁻⁻⁴. So S4KL means that this quantity is of the order C⁻⁴. Pi2 means that it is the quantity of the order C⁻², and so on.
Jest strzałek lewa, prawa na laptopie.
Aha. Maybe it's too late. Too late. You see, the expert, the BIM expert knew what he was saying. No subsections in the BIM, please remember.
Za bardzo?
Za bardzo. Zdecydowanie za bardzo. O, tutaj.
Tutaj, tu. Konserwatywna.
Tak?
Tak, lewa. I jak pan używa tego, to jak dochodzi do tego ekranu z subsekcjami, to pan wywala na początek prezentacji. Dlatego trzeba od początku przewiedzieć.
Tylko ja nie wiem, kiedy to się pojawi. Ja takiego dobry to ja nie jestem. Okay, sorry. Okay, and now, as I have said, we will treat differently the conservative section of the dynamics and the dissipative section of the dynamics. So we start from the conservative matter Hamiltonian. So our final goal is to have the Hamiltonian which depends only on the matter variables. That is, only on XA and PA, only on positions and momenta of the particles. How to do this? There are several stages. The first one is to go to the Rauthian. The Rauthian is defined here. It is the function which is Hamiltonian with respect to the matter variables and Lagrangian with respect to the field variables. And it is defined in an usual textbook way. This is the first stage. Why are we doing this? Because then at the very end, we are able to prove just by direct computations that the final equations of motion has the standard Hamiltonian form. Without this stage, it would not be possible to do this. Okay, the second stage is elimination of the field variables, now HTT and HTT dot. Of course, over dot means, but you know all this differentiation with respect to time. They are integrated out, that is replaced by time symmetric solutions of their field equations. And here we already exclude any radiation effects.
So time symmetric is
Half. It means that we use green function, which is half advanced, half retarded. In a moment, I will say more about this. So formally, we obtain something which depends only on matter variables, yes, because we replace field variables by the explicit solutions of their field equations. But what is still interesting, maybe, I'm not sure, is that because of this time differentiation and not only of this, also because of the further expansion of these functions related with the retardation in it, they depend on not only on the positions and momenta, but also on derivatives of the position and momenta. But this is a well-known problem. We can just use the lower level equations of motion to eliminate this. And this is exactly equivalent to making just a canonical transformations in the phase space of the problem. So time derivatives of positions and momenta are not problematic. So finally, we have something like this. We can say that this is the conservative Hamiltonian, which depends only on positions and momenta. It can be derived from this action, if you want. All is very usual. Okay, but now we need these time symmetric solutions. So again, here we have the field equations for the TT. And if we need the time symmetric solution, I have said we should use this half advanced, half retarded green function. But to compute this, we have to make the next step. Namely, we have to expand this formally in the post-Newtonian manner. It means that instead of this operator, we have something like this, where we symbolically use the inverse Laplacian operators and their powers as well. And lack of this combination means that in this expansion, we have only even powers of the time derivatives. So this is why we have no chance to produce the radiative effects. Okay, if we do this, then we should also post-Newtonian expand the source term. Yes, and then we can obtain HTT as a post-Newtonian series as well. And up to 4pn and including 4pn level, it is enough to take the leading order solution, which I have shown already you some slides before, and the next one, which is C2 minus 6. Okay, but because of presence of the higher order inverse Laplacians, HTT6 behaves very nasty at spatial infinity. Namely, it contains a part which behaves like R in 3 dimensions. And because of this, we have some infrared divergences. And as I have said, to regularize them, we need some new length scale, which I will denote SIR. Okay, so after replacing HTT by this solution, which is obtained because of this double post-Newtonian expansion, first the post-Newtonian expansion of the green functions and then of the source terms, we obtain Hamiltonian, which is a usual Hamiltonian. It is a function of positions and momenta, but this is not the whole Hamiltonian. It is only the so-called near zone Hamiltonian. Why? Because by post-Newtonian expansion of the green function, we lost what is called in general relativity tail effects. We have to add tail effects by hand. As you know, tail effects are related with the backscattering of the gravitational waves. If the system is emitting gravitational waves, they are scattered back by the, say, space-time curvature, going back to the system and modify both their motion and their radiation as well. And of course, what is radiated by tails is scattered back, and we have tail of tails, tail of tails of tails, and so on. But fortunately, this structure also is well expanded within the post-Newtonian scheme. But anyway, at this moment, in which we make the post-Newtonian expansion of the green function, we lose these tail effects. But look first more carefully at this near zone contribution to the total Hamiltonian. This near zone contribution develops both UV and infrared divergences. But what is not obvious and computational is quite involved, you can split this Hamiltonian into two parts. The first part is infrared convergent, but it develops UV poles. So regularization is also related to the UV poles. And the second part is vice versa. That is, it is infrared divergent by UV convergent. And for this part, we need this new regularization scale. Okay. And now that we need to add by hand, Taylor relative contribution was known from this paper at least, in which the authors showed that exactly starting at the fourth Post-Newtonian level, it is not possible in any gauge, this is a gauge-independent feature, it is not possible to express near-zone metric as a function of the instantaneous positions and momenta in our formalism of the particles, of the source. In general, because this is the more general paper, not assuming that we have to deal with that we have a two-point particle system, this is the general feature. So the fourth Post-Newtonian metric is just the sum of the instantaneous functional and non-local in time Taylor contribution. This non-locality in time is not very strange, yes, because the interaction of Tails with the system depends on the history of the wave, which was scattered somewhere in the space-time, then went back to the vicinity of the source and interact with it. And here we try to use this information, and the main result was that they computed this Taylor related contribution to the metric in any gauge. By to do this, they had introduced some arbitrary length scale, which is, say, the intermediate length scale between the size of the system and the reduced wavelength of the gravitational wave which the system is producing. So we had at our disposal some metric, and it was not very difficult to translate the contribution to the equations of motion due to this metric into the extra Hamiltonian. Yeah, this is just to put this contribution in the Hamiltonian language. And the Hamiltonian looks as follows. Of course, the Taylor contribution also, as I have said, modifies the radiation reaction. Yeah, so we need here only the, again, time symmetric part of this Taylor-related contribution. And this is given by this strange formula in 3 dimensions. So at the moment of the completing the fourth Post-Newtonian Hamiltonian, we had at the disposal only this 3-dimensional result. Here, Ij is just the Newtonian quadruple moment of the binary system defined here. Triple dot means just the third time derivative of this. But as you can easily see, this integral is divergent at v equal to 0. So you have to use Hadamard-Parti-Fini procedure. And this is the definition how to do this. Namely, if you have some scale t and you have such divergent integral, the Hadamard-Parti-Fini of this integral means that you are doing the following thing. The interval from minus to plus infinity split into 3 parts, namely from minus infinity to minus t, from minus t to plus t, and from t to plus infinity. These 2 contributions are fine. We assume that g of v behaves nicely at infinity. both positive and negative infinity. And here we are doing the following thing. We are just assuming that g of v is finite at v equal to 0, what is the case. And we are just subtracting the g of 0 to give the function which is linear in v when v goes to 0. So in this way, we just cancel the 1 over v singularity here. And the result is finite. In fact, this formula follows from the nicer formula for the total tail effect, which is finite. And then no such tricks with this Hadamard-Platini is not needed. But if you would like to split the full tail effect into time symmetric and the rest, then you need this operation. And now we do something what is now obvious for all, but then it was not obvious at all, that we should relate the infrared regularization scale with this regularization scale related to the tail effects. It means that there is a close collaboration between the tail effects and infrared divergence of the near zone expansion of the metric. As I said, now it is almost obvious for all, but at the moment it was not so obvious. There are some, say, computational hints why this is true. I will show you in a moment. So finally, our conservative Hamiltonian is the sum of two pieces of the near zone Hamiltonian with just an usual function of position and momenta, and a tail-related Hamiltonian with a functional of the trajectories in phase space. Yeah. Oh, too late again. Maybe not too late. Okay. Okay, I have 5 minutes. So 5 minutes is 5 minutes. It's a lot of time. So let us start this dissipative stuff. What I will talk here is quite simplified, but if you would like to have some more refined treatment, it can be found in this review article, in section 3 of this review article. But finally, this treatment also boils down to what I will explain you now. Namely, if we are interested in the near zone expansion of the retarded, if we are interested in the dissipative effects, we should use the near zone expansion of the retarded solutions. So not exclude radiation effect. And then, as you see, HTD contains some extra terms. Yes, for time symmetric solution, we had only this function and that function. Here we have also function at odd powers in 1 over c. The same is with the field momenta. This is what follows from the time symmetric part of the solution. Here there is one difference. This is difference of 1 in the 1 over c because this contains always time derivative of this function. And what is interesting that these functions are responsible for the time irreversibility of the equations of motion, exactly these terms. But let us start from the split of the total Hamiltonian to the in a different way. Namely, we have matter part, which depends only on the matter variables. We have interaction part, which depends on both matter and field variables. And then we have purely field part of the Hamiltonian. Then we just dropping the field part of the Hamiltonian. So we use some new Hamiltonian H tilde, which contains only matter and interaction part. Because, you know, if we have the full Hamiltonian, then it is conserved. But we expect that there is some flow of energy between the matter and the gravitational radiation. So we are making such a trick that after dropping this field part, we have only matter part and interaction part. So we expect that in this, we should this flow somehow observe. And this tilted Hamiltonian can be represented as the sum of the conservative part and the dissipative part. And the conservative part contains all what we already discussed, namely Newtonian 1p and 2p and 3p and Hamiltonians, whereas this dissipative part is a new part, which contains up to this 3.5p and order 2 terms. And now is the final trick, namely, again, we treat this as a matter-only Hamiltonian. This is okay, because we can always replace HTT and PyTT by their solutions, and these solutions are just functions of XA and PA. But we distinguish this XA and PA inside these functions from this which are outside. We treat this as a function which, from point of view of the Hamiltonian, depends explicitly on time. So in this way, we introduce dissipation. It is not very uncommon to use two sets of variables, because then you see in the concrete computations, it is a bit devil, because you have to distinguish XA outside the TT variables and inside, but to make any computation, you have to use the explicit form of this as a function of XA and PA. So this is quite tricky to do this, but anyway, you can do this. And I think I will stop because we have already 5 and it's enough for today. I will continue tomorrow. Thank you for the attention.
Can I ask a question?
Oh, yes. Of course.
Hello, thank you. So, I mean, you have to introduce all these regulators, particularly the infrared ones, and also in the Parthi-Fini of the Hadamard and so on. So all these formula have the regulator built in. They depend on the choice of regulator. But the final answer should be the regulator independent, because you give me. So how do you remove that regulator? This
will be the subject of my next lecture. But yeah, but of course, after identification of this infrared scale with the Taylor-rated scale, they disappear from the final result, exactly, algebraically. But our problem was that the way in which we regulate infrared divergences is not unique. We have found some ambiguity.
Right.
This ambiguity is not present in effective field theory approach, for example, because they use also for infrared divergences only dimensional regularization scale, and they use d-dimensional version of the tail contribution, and it is enough. After many years, it has appeared that it is enough to use pure dimensional regularization, but not in our formalism, unfortunately.
I see. So in your formalism, it's an input. Is that right? That somehow there is some extra input which tells you that the term disappears. The regulator disappears.
No. The regulator disappears within the formalism, but the result is ambiguous. But
yeah, that's what I mean. So to remove the ambiguity.
But the ambiguity does not depend on this regulator. It is just one unknown number.
Right, but okay. Yeah, but I mean, in my view, it is really coming because of the way that the regulator is treated. I mean, because why should there be an ambiguity? It is because one had introduced a regulator. If in fact everything was finite, there would be no ambiguity. So that to me, at least, the origin of the ambiguity is always in the choice of regulator. But if you think that's not the case, then we should discuss privately somehow.
Okay, and in fact, you are right, but this is because situation is such that this constant can be interpreted as a change of the value of the scale.
Right.
Okay.
Exactly.
So
Exactly.
I am right and you are right.
Okay. Yeah. So yeah, what you said is exactly what I was saying. That this would be just
yeah.
the scale is the ambiguity.
Okay.
Okay. Thank you.
That is captured by the dissipated part. Where does it end up? Well, dissipation should remove the energy. So
In gravitational waves, of course. And this is the way in which we can compute the luminosity. This is the start of my next lecture. Yeah, and yeah. You will see at the beginning of the next lecture how to do this. This is, you see, this is textbook solution now. If your Hamiltonian is explicitly dependent on time, then you know that the change of the energy is just expressible as a partial time derivative of Hamiltonian with respect to time, using only the explicit dependence on time. That's all. And then you have to average this, and you have the luminosity in gravitational waves. So this is conceptually extremely simple compared to the usual way of computing this, but unfortunately, calculation is not easy.
yeah, that is why it's only odd powers and odd orders that we can anticipate.
You mean of odd powers of what?
So the part was not at all powers of Pn, but some.
No, this is more complicated. This nice splitting is up to 3.5 Pn. Starting from 4 Pn, in equations of motion, you have part which is conservative and part which is dissipative. There is a mixture of this, unfortunately.
So up to this lower levels, then can we say why this is the case?
It follows directly from Einstein field equations. I don't know why. The gods decided that the radiation start at 2.5 Pn. This is just by simple algebraic counting of 1 over c in the equations. It could start at 3.5 Pn. Why not? But it is not the case. I don't know why. This is a very deep philosophical question, I think. Why there is a shift between radiation dissipation and the conservative by 2.5 Pn order. Exactly 2.5, not 3.5, not 4. I don't know why.
So here, so it said that the luminosity is supposed to be calculated on the energy loss.
Yes.
But this is total luminosity. What do you want to get the angular calculus?
You see, angular dependence. I haven't thought about this, thinking, but I think that it is possible to do this. I haven't. You see, I think it is possible. No, I don't know by heart, but it is not very interesting from point of view of application to gravitational wave astronomy, yeah, because the whole luminosity is what modify the motion of the source, yes.
Observed by gravitational wave detectors, then it's important the source emits
Yes, but you observe HTT, not the luminosity. This is a completely different story. From luminosity to HTT, there is some, you see, route to be covered. So it is not so. You observe HTT, not HTT.
Thank you.